When querying a relational database, it's often necessary to bring together information from multiple tables. The query language SQL lets us join tables in various ways. In this video, we'll explore the joins that are possible in SQL: inner joins, left and right outer joins, full outer joins, and cross joins. By the end of this video, you'll understand what these different types of joins are for and how you can usefully apply them. This is Decomplexify, bringing a welcome dose of simplicity to complex topics. Let's suppose we have a database that records information about chemical compounds and the chemical elements that make them up. An example of a chemical compound is water. Water, as we all know, is H2O, meaning a water molecule consists of 2 hydrogen atoms and 1 oxygen atom. In our database, we capture this kind of information about compounds and their atomic ingredients in 3 tables: a compound table to record compounds like water, an element table to record elements like hydrogen, and a table which we'll call compound element details, which tells us about the elements each compound is made up of. Of course, many more compounds and elements exist than the ones we've listed, but for the sake of simplicity, let's assume that the only elements and compounds we need to deal with are the ones shown here. Suppose someone asks us this question: what are the names of compounds that contain the element called hydrogen? To answer this question, it's not going to be enough to consult the compound table. The compound table tells us the names of different compounds, but it doesn't tell us what elements they contain. What if we consult the compound element details table instead? The compound element details table is helpful in that it tells us about the elements that make up each compound, but still it doesn't quite give us what we want because it doesn't give us names of compounds, only compound IDs. And similarly, it doesn't give us names of elements, only element symbols. The challenge we have is that the answer we're looking for can't just be obtained from one table. Instead, it has to be deduced from information in all 3 tables. Let's see how this works. The compound element details table tells us that the element designated by element symbol H is contained in compound ID 100. The compound table tells us that compound ID 100 is water. From these 2 pieces of information, we can deduce that the element designated by element symbol H is contained in water. Now let's go further. If we look in the element table, we can see that the element designated by element symbol H is hydrogen. From this piece of information, plus what we already know, we can deduce that hydrogen is contained in water. Let's apply this same process of logical deduction to every other row in the compound element details table, with the aim of getting to a comprehensive list of which element names are associated with which compound names. To do this, we work through the rows of the compound element details table. Wherever we see a compound ID 100 in compound element details, we put the corresponding 100 row from compound next to it. Whenever we see a compound ID 101 in compound element details, we put the corresponding 101 row from compound next to it, and so on. And similarly with element. Whenever we see element symbol H in compound element details, we put the corresponding H row from element next to it. Whenever we see element symbol C in compound element details, we put the corresponding C record from element next to it, and so on. The operation we've carried out here is called a join. More specifically, it's called an inner join. The word inner signifies that we are only interested in successful matches. In other words, the results of the join shouldn't include any compound element details row whose compound ID fails to match a compound ID in the compound table. And similarly, it shouldn't include any compound element details row whose element symbol fails to match an element symbol in the element table. This is why compound ID 104, known as mystery compound, doesn't appear in the join results. In the compound element details table, compound ID 104 has two rows, one with element symbol Q and another with element symbol X. Q and X both fail to match any element symbols in the element table. It seems fair to say that this is a problem with the data, and that the people in charge of the data really ought to fix this in the future. But for now, the important thing to highlight is that because element symbols Q and X fail to match anything in the element table, the inner join ensures that the compound element details rows that feature element symbols Q and X don't make their way into the result set. Each of the glued together rows that result from joining the three tables together can be interpreted as a statement about compounds and elements. For example, the first row signifies that the compound with compound ID 100 is called water, and that a molecule of it contains two atoms of the element with element symbol H, which means hydrogen. And the second row signifies that, once again, the compound with compound ID 100 is called water, and also that a molecule of it contains one atom of the element with element symbol O, which means oxygen, and so on. Finally, we are in a position to answer our question, what are the names of compounds that contain the element named hydrogen? To do this, we look in our join results and find the rows that have element name equals hydrogen. There are two such rows, one for compound name water, and another for compound name ammonia. With all this in mind, let's translate the question, what are the names of compounds that contain the element named hydrogen, into an SQL query. And as a bonus, let's write the query in such a way that its output shows us the compounds' IDs as well as their names. The clause from compound element details CED signifies that one of the tables we're interested in is the compound element details table, and that throughout the rest of the query, we're going to be referring to that table by the nickname or alias CED. The clause inner join compound C on CED.compoundID equals C.compoundID signifies that we're joining the CED table to the compound table, nicknamed C, in a way that matches the compound ID from the CED table to the compound ID from the C table. The clause inner join element E on CED.elementSymbol equals E.elementSymbol signifies that we're also joining the CED table to the element table, nicknamed E, in a way that matches the element symbol from the CED table to the element symbol from the E table. In the output of the join, each CED row is shown with the corresponding E row information and C row information glued onto it. The output of the join gives us a good basis for answering our question. But as the question asks specifically about hydrogen, we need to ignore all the rows in the join results that aren't about hydrogen. Doing this doesn't require us to change anything about how we're doing our join, but it does require us to add a filter condition at the bottom of our query. This takes the form of a where clause, where E.elementName equals hydrogen. Finally, when it comes to answering our question, we don't care about every single column from every one of the three joined tables. For example, we're not interested in the number of atoms column. We're only interested in compound ID and compound name from the compound table. So we ask the database to show us just those columns. This is the result we were looking for, compounds containing the element called hydrogen. Now let's turn to a different question. The question is, which elements don't belong to any compounds? To answer this question, we'll attempt to relate rows in the element table to rows in the compound element details table. Specifically, for every row in the element table, we're going to look at that row's element symbol, and we're going to try to find all the compound element details table rows that have that same element symbol. If, for example, the row that we're looking at in the element table has element symbol H, then we're going to try to find every compound element details row that also has element symbol H. When we find a match, we're going to glue the element row to its corresponding compound element details row, and include this glued together row in our join results. Unfortunately, this kind of matching isn't yet sufficient to help us to answer our question. Remember, our question was which elements don't belong to any compounds. So the successfully glued together rows, signifying elements that do belong to compounds, are of no interest to us. We need to carry out our matching in such a way that even if an element row fails to match any compound element details rows, we still bring it into our join results. And when we bring it into our join results, we'll show it glued to a blank or empty compound element details row. This kind of join, which ensures that the results include unmatched rows as well as matched ones, is called an outer join. In an outer join, it's important to keep straight which table we're matching from and which table we're matching to. Remember, in an outer join, when we're matching from table A to table B, and a particular row in table A fails to match anything in table B, the row from table A still gets included into the join results. In short, all of table A's rows will be included in the join results, regardless of whether they match something or not. In the outer join we want to do, the table we're matching from is element, and the table we're matching to is compound element details. The clause from element E signifies that one of the tables we're interested in is element, and that throughout the rest of the query we're going to be referring to the element table by the nickname E. The join to compound element details CED on E.element symbol equals CED.element symbol signifies that for each row in table E, the element table, the database platform will look at that row's element symbol and try to find rows with that same element symbol in the table CED, the compound element details table. If it succeeds in finding matching rows in table CED, then it's going to return each matching CED row with the corresponding E row information glued onto it. In other words, the join gives us all matching combinations of E rows and CED rows, matching in the sense of sharing the same value of element symbol. But that's not all the join gives us. The join also gives us rows from table E that failed to match any rows in table CED. And the reason it does this is that it's a left outer join. The phrase left outer join tells the database platform that the table we're matching from is the table on the left side of the join expression, in this case, element. Because element is the table we're matching from, all of the rows from element will make their way into the join result, regardless of whether they match a compound element details row or not. If this is a left outer join, what's a right outer join? The answer is that a left outer join of element to compound element details is exactly the same as a right outer join of compound element details to element. They are simply two ways of expressing the same thing. Here is how our query would look as a right outer join. In this way of expressing it, the table we're matching from is the table indicated on the right of the join expression, again, element. Because every right outer join can be rewritten as a left outer join, and because left outer joins read a little more naturally than right outer joins, there is in fact never any need to use right outer joins at all. Incidentally, some people prefer to use the slightly abbreviated keywords left join and right join instead of left outer join and right outer join. The use of the word outer is optional. Let's look at the results of our left outer join. The meaning of the first row is the element with element symbol H is called hydrogen, and 2 atoms of it occur in a molecule of compound 100. The meaning of the second row is the element with element symbol H is called hydrogen, and 3 atoms of it occur in a molecule of compound 102. Now let's skip down to the last row, the one for element symbol He. There weren't any matching rows in compound element details for element symbol He, so there simply are no applicable values for compound ID or number of atoms on this row of the join results. In SQL, the absence of a value is represented by a symbol called null. The concept of null in SQL has always been controversial, as nulls in SQL databases lead to a number of logical difficulties. But discussing these difficulties is not part of the scope of this video. When it comes to joins, the important thing to keep in mind is that on the helium row in the join results, compound ID is shown as null because helium had no matching compounds. Or, to put it in real-world terms, the element helium doesn't occur in any compounds. And so, if we want our query to answer the question which elements don't occur in any compounds, we need to look for those null compound IDs. This is done by tacking a where clause onto the end of our query. Next, we turn to the topic of full outer joins. What if we want to join between table A and table B that gives us not only what the left outer join gives us, table A rows that don't match anything in table B and table A rows that do, but also table B rows that don't have matches in table A. A join like this is called a full outer join, A full outer join B, or equivalently B full outer join A. Full outer joins are very rarely necessary in practice, and the meaning of a set of full outer join results is a little awkward to express. If we were to do a full outer join of element to compound element details, like this, we would get these results. Most of the rows returned have proper values in both the columns from element and the columns from compound element details. But the helium row doesn't. As we saw in the left outer join example, this row means the element with element symbol He is called helium, and it doesn't occur in any compounds. What about the row that has CED element symbol Q? It means something like the compound with ID 104 contains 2 atoms of an element with symbol Q, but we have no information about what element the symbol Q is supposed to represent. And the row with CED element symbol X can be interpreted along the same lines. So far, all our join conditions have simply been about matching the value in a column of one table to a value in the column of another table. For example, E.element symbol equals CED.element symbol. But a join condition in SQL doesn't have to look like that. In fact, the join condition can be any condition whatsoever. Suppose we have a person table and an animal table, and we want to know, out of all the possible combinations of one person and one animal, which combinations have a combined age of less than 47. Then we can do a query like this. In this case, out of the 9 possible combinations of person row and animal row, the database platform returns only those combinations that qualify as a match, based on the match criterion that the total of person age and animal age should be less than 47. But what if we simply want to see the full list of those 9 possible combinations of one person and one animal without any further restrictions? To get a list of the combinations, we can specify a join condition that always evaluates as true, like this. Because the join condition is always going to be true no matter what, every row from person is going to get matched to every row from animal, and we're going to get a result set consisting of all 9 person-animal combinations. This kind of result, which consists of every possible combination of the rows from one data source with the rows from another data source, is known as a Cartesian product. And although specifying a join condition that always evaluates as true, like 1 equals 1, will give us a Cartesian product, a more concise way of expressing the same thing is to use a type of join expression called a cross join. The cross join will give us the 9 rows we want to see, and notice that we don't need to specify a matching criterion for the cross join of person to animal, because the whole point of a cross join is that every row from one table is going to get matched, unconditionally, to every row from the other table. A final point to make is that whichever types of join you use, there are no restrictions on what tables these joins can operate on. You can even join a table to itself. When might we want to do this? Well, suppose we have an employee table that looks like this. Every employee has an approver who is also an employee. The approver is a person who can approve the employee's requests for days off. For example, Pam's approver is employee 4, Elsa. Notice that the employee, Olivia, is so senior that she can approve her own requests for days off. Her approver is employee 6, herself. Let's write a simple query that lists all employees along with the names of their approvers. Here is the query. And here are the results it returns. The inner join used in this query is fundamentally no different from any other inner join. It just happens that in this case, we're matching each row from the employee table to a row in the employee table. We are, in effect, joining from one copy of the employee table to another copy of the employee table. We give the first copy a nickname of E, and we give the second copy a nickname of AP. For each row in E, we want to find the row in AP whose employee number matches the E row's approver employee number. And this is why the join condition is E.approver employee number equals AP.employee number. This completes our discussion of joins. I hope you found it helpful. If you have any comments or questions on what you've just heard, please go ahead and post them in the comments section below. And if you have any suggestions for other complex topics that you'd like to see explained on Decomplexify, let me know in the comments. Feel free to like, share, and subscribe. So long, and thanks for watching.